27.3 Kirchhoff's rules. In this lesson, we will explore the fundamental principles used to analyze complex electrical circuits. We begin with an introduction to complex circuits and why standard reduction methods sometimes fail. We will then define Kirchhoff's two primary laws, the junction rule and the loop rule. To apply these rules accurately, we must establish specific sign conventions for potential differences across resistors and batteries. Finally, we will outline a formal problem-solving strategy and walk through worked examples for both single-loop and multi-loop circuits to see these rules in action. While many simple circuits can be simplified by combining resistors in series or parallel to find an equivalent resistance, many real-world circuits are more complex. As you can see in the diagram, which features multiple resistors and batteries, the presence of an additional 18-volt battery in the left branch prevents us from reducing the system to a single loop using basic rules. When we encounter such a network where components are not clearly in series or parallel, we must rely on Kirchhoff's rules to solve for the unknown currents and potential differences in each branch of the circuit. Kirchhoff's first rule is the junction rule. It states that at any junction point in a circuit, a point where three or more wires meet, the sum of the currents must equal 0. This is a direct consequence of the conservation of electric charge. Since charge cannot accumulate or vanish at a point, the total charge entering a junction must equal the total charge leaving it. By convention, we treat currents directed into the junction as positive values, and currents directed out of the junction as negative values. This allows us to write a simple algebraic equation for every junction in the network. To better understand the junction rule, we can look at a mechanical analog, water flowing through a branched pipe. In the illustration, water flows in from the left and splits into two paths. Just as water does not leak out of the pipe, the flow rate in must equal the total flow rate out. In the electrical circuit diagram labeled A, the current I sub 1 enters the junction, while I sub 2 and I sub 3 leave it. Following our convention, we write the equation as I sub 1 minus I sub 2 minus I sub 3 equals 0, ensuring that the total charge is conserved. The second rule is Kirchhoff's loop rule, which is based on the conservation of energy. It states that the sum of the potential differences, or voltages, across all elements around any closed circuit loop must be 0. This works because the electric force is conservative. Just as a hiker returning to their starting point on a mountain ends at the same elevation, a charge moving around a complete loop and returning to the same point must return to the same electrical potential. Therefore, the sum of all potential increases must exactly balance the sum of all potential decreases. To apply the loop rule, we must be very careful with signs. When traversing a resistor in the direction of the current, the potential decreases, so the change in voltage is negative I times R. If you move against the current, the potential increases, giving A positive I times R. For batteries, or sources of electromotive force represented by epsilon, the sign depends on the direction of travel relative to the battery's terminals. If you move from the negative terminal to the positive terminal, the potential increases by plus epsilon. If you move from the positive to the negative terminal, you are going against the EMF direction, resulting in a change of minus epsilon. These rules are named after Gustav Kirchhoff, a prominent 19th century German physicist and professor at Heidelberg. While he is famous in circuit theory, his contributions to science were vast. Along with Robert Bunsen, he invented the spectroscope and founded the science of spectroscopy. This work led to the discovery of the elements cesium and rubidium. His laws of circuit analysis remain the bedrock of electrical engineering, providing a systematic way to solve for currents in even the most intricate networks. When tackling these problems, follow this four-step strategy. First, conceptualize. Identify all circuit elements and the polarities of the batteries. Second, Categorize. Check if you can use simple series or parallel rules. If not, proceed with Kirchhoff's rules. Third, analyze. Start by arbitrarily assigning directions to the currents in each branch. Apply the junction rule to all junctions except one. Then apply the loop rule to independent loops until you have enough equations to match your number of unknowns. Finally, solve the equations. If a calculated current is negative, it simply means the actual flow is opposite to your initial guess. Let us look at example 27.6. A single loop circuit with 2 resistors and 2 batteries in opposition. We start at point A and travel clockwise. Crossing the first battery from negative to positive gives plus epsilon 1. Moving through the first resistor with the current gives minus I times R1. Crossing the second battery from positive to negative gives minus epsilon 2, and the final resistor gives minus I times R2. Setting the sum to 0 and plugging in the values of 6 volts, 12 volts, 8 ohms and 10 ohms, we find a current of negative 0.33 amperes, meaning the current actually flows counterclockwise. In example 27.7, we analyze a multi-loop circuit to find 3 unknown currents. We start at junction C and apply the junction rule. I1 plus I2 minus I3 equals 0. Next, we choose 2 independent loops to traverse clockwise. For loop ABCDA, the equation involves the 10-volt battery, the 6-ohm resistor, and the 2-ohm resistor. For loop BEFCB, we move through the 14-volt battery and the 4-ohm and 6-ohm resistors. This gives us a system of 3 independent equations that relate the currents to the known voltages and resistances in the branches. To finish the multi-loop example, we solve the equations simultaneously. By substituting the junction equation into the first loop equation, we reduce the system to 2 variables. Solving these yields a current I2 of negative 3.0 amperes and I1 of 2.0 amperes. Finally, using our junction rule, we find I3 is negative 1.0 ampere. The negative signs for I2 and I3 tell us that these currents are actually flowing in the direction opposite to what we initially assumed. This highlights the importance of consistency. As long as you stick to your initial directions during the math, the results will be correct. In summary, Kirchhoff's rules are essential tools for analyzing circuits that cannot be simplified using standard resistor combinations. The junction rule is rooted in the conservation of charge and ensures that the total current entering a point equals the total current leaving it. The loop rule is based on the conservation of energy and the conservative nature of the electric force, ensuring the total potential change around a loop is 0. Mastering these rules requires consistent application of sign conventions for resistors and batteries during the analysis phase. To conclude, let us reflect on 2 key points. First, think about the physical conservation laws we discussed. Which one specifically provides the foundation for Kirchhoff's second rule, the loop rule? Second, consider the geometry of a circuit. If you have a complex network with n distinct junctions, what is the maximum number of times you can apply the junction rule to generate equations that are mathematically independent? Understanding these theoretical limits will help you solve complex circuit problems more efficiently in the future.